We can derive the product rule by just going back to the definition of derivative. So what does the definition of derivative say? It tells us that the derivative of the product of f of x and g of x is a limit. It's the limit as h approaches 0 of the function at x plus h, which in this case is the product of f and g, both evaluated at x plus h, because I'm thinking of this as the function. So I'm plugging in x plus h. And I subtract the function evaluated at x, which is just f of x times g of x, and I divide that by h. So it's this limit of this difference quotient that gives me the derivative of the product. How can I evaluate that limit? Here's the trick. I'm going to add a disguised version of 0 to this limit. Instead of just calculating the limit of f of x plus h times g of x plus h minus f of x times g of x, I'm going to subtract and add the same thing. So here I've got f of x plus h times g of x plus h, just like up here. Now I'm going to just subtract f of x plus h times g of x and then add it back in, plus f of x plus h times g of x. This is just 0. I haven't done anything. And I'm going to subtract f of x times g of x right here, and I'm still dividing by h. So these are the same limits. I haven't really done anything, but I've actually done everything I need. By introducing these extra factors, I've now got a common factor of f of x plus h here and a common factor of g of x here. So I can collect those out and I'll get some good things happening as a result. Let's see exactly how this happens. So this is the limit as h goes to 0. I'm going to pull out that common factor of f of x plus h. And I'm going to multiply by what's left over, g of x plus h minus g of x. And I can put it over h. So that's these two terms. Now what's left over here, I've got a common factor of g of x. And what's left over, f of x plus h minus f of x. I'll divide this by h. And then the factor I pull out is g of x. So this limit is the same as this limit. Now this is a limit of a sum. So that's the sum of the limits provided the limits exist. And we'll see that they do. So this is the limit as h goes to 0 of f of x plus h times g of x plus h minus g of x over h plus the limit as h goes to 0 of f of x plus h minus f of x over h times g of x. Now what do I have here? I've got limits of products, which are the products of limits provided the limits exist. And they do. We'll see. So let's rewrite these limits of products as products of limits. This is the limit as h goes to 0 of f of x plus h times the limit as h goes to 0 of g of x plus h minus g of x over h. You might begin to see what's happening here, plus the limit as h goes to 0 of f of x plus h minus f of x over h times the limit as h goes to 0 of g of x. Okay, now we've got to check that all these limits exist in order to justify replacing the limits of products with the products of limits. But these limits do exist. Let's see why. This first limit, the limit of f of x plus h as h goes to 0, is actually the hardest one, I think, of all these to see. Remember back, we showed that differentiable functions are continuous. This is really calculating the limit of f of something as the something approaches x. Right? That's really what this limit is. And because f is continuous, because f is differentiable, this limit is actually just f of x. But I think seeing that step is probably the hardest in this whole argument. What's this thing here? Well, this is the limit of the thing that calculates the derivative of g. And g is differentiable by assumption. So this is the derivative of g at x. Plus, what's this limit? This is the limit that calculates the derivative of f. And f is differentiable by assumption, so that's f prime of x. This is the limit of g of x as h goes to 0. This is the limit of a constant. Wiggling h doesn't affect this at all, so that's just g of x. And look at what we've calculated here. The limit that calculates the derivative of the product is f of x times g prime of x plus f prime of x times g. That is the product rule. What have we really shown here? Well, here's one way to write down the product rule very precisely. Confusingly, I'm going to define a new function that I'm calling h. So h is just the product of f and g now. H of x is f of x times g of x. If f and g are differentiable at some point a, then I know the derivative of their product. The derivative of their product is the derivative of f times the value of g plus the value of f times the derivative of g. This is a precise statement of the product rule. And you can really see, for instance, where this differentiability condition was necessary. In our proof, at some point in the proof here, I wanted to go from a limit of a product to the product of limits. But in order to do that, I need to know that this limit exists. And that limit is exactly calculating the derivative of g. So you can really see where these conditions are playing a crucial role in the proof of the product rule.